Welcome back, student. In the previous lecture we have gone through the lossless and distortionless line. This is the time to discuss now about next point of the topic, that is reflection coefficient and open and short circuited line, reflection factor and reflection loss, standing wave nodes, and all other things of this particular unit. So these things you need to understand, because this is correlated terms, because reflection, then reflection coefficient, then standing wave ratio, input impedance, all these things are correlated terms. So from this point onward we'll take a distortionless line for our understanding, because we are going to assume from this point onward that transmission lines are distortionless. That means we assume that alpha is independent of the frequency and beta is a linear function of the frequency, and we consider characteristic impedance to be of the real value. It will have certain real value, 50 ohm, 100 ohm, 150 ohm. It will not have a value of 150 plus j something or 50 plus j something. So from this point onward we are going to have a discussion about distortionless line or dissipationless line. So let's talk about this now. Voltages and current on dissipationless line. We already know for a dissipationless line alpha is equal to 0. So let's go back to the certain expressions of the transmission line which we already studied. The value of the voltage. So the voltage at any point distance units from the receiving end of the transmission line is given by, it is E is equal to ER into ZR plus Z0 divided by 2 ZR inside bracket e raised to gamma s plus k e raised to minus gamma s. Now what is this k? Okay. So if you do remember, we have written certain different forms of the transmission line equation even in the physical significance. We came to the conclusion that it can be written as e raised to root zys. Just try to remember this equation. It will be under root of zy into s plus zr minus z0. Okay, I'm just writing it here for your understanding. Zr minus z0 upon zr plus z0 into e raised to under root of minus zy into s. So certain equation something like this. So I have just replaced in this equation under root of zy by gamma. So it look like e raised to gamma s plus, and this k corresponds to reflection coefficient. What is reflection coefficient? Reflection coefficient will give us the amount of wave that is being reflected from the load towards the source. If I just draw a transmission line, so waves start transmitting from this point onwards, it comes to a load at this point, and once again it start traveling back into the towards the source direction. So how much amount of wave is being reflected to the amount of wave which is being transmitted is nothing but our reflection coefficient, which will be denoted by either k or it can be represented by capital gamma also. So capital gamma notation, I will once again draw it for you. Capital gamma notation is something like this. Okay, so this is small gamma, this is small gamma, and this is capital gamma. Don't confuse. So this is small gamma and this is capital gamma. Capital gamma is so don't not to have a confusion between small gamma and capital gamma, we are just representing the reflection coefficient by the term k. So k represent amount of wave being reflected to the amount of actual amount of wave which is being incident in terms of voltages. So this zr minus z0 upon zr plus z0 is called a reflection coefficient of a wave, and it can be represented by either k or capital gamma. Okay. So once this reflection coefficient concept is clear, can I write this equation as E is equal to ER ZR plus Z0 divided by 2 ZR inside bracket e raised to gamma s plus k e raised to minus gamma s, where k is the reflection coefficient. For a line to have a zero dissipation, attenuation constant alpha is 0 and Z0 equal to R0. So wherever I am finding Z0, I can replace it with the R0. That we already know that if Z0, okay. So this is the expression we have written. E is equal to ER into ZR plus R0 upon 2 ZR e raised to j beta s plus k e raised to minus j beta s. Since alpha is equal to 0, we have replaced this gamma term as alpha plus j beta, that you already know. If alpha is equal to 0, we come to this particular point. It may be a repetition for you, just but try to understand. So this is the expression we have got by representing gamma as alpha plus j beta, and if alpha is equal to 0, it will become j beta s plus k e raised to minus j beta s. Okay, the next thing, the term varying with e raised to j beta s, because there are two terms here. The one which is varying in e raised to plus j beta s and e raised to minus j beta s. We already know the basics of the wave equation, which tells me that if I get the equation e raised to plus j beta s, that represents the wave traveling in the minus s direction. If I am getting expression of e raised to minus j beta s, that means wave which is traveling in the positive s direction. But what is positive s and negative s direction? Let's try to draw a certain diagram so that you will understand. If this is a transmission line, always distance is taken from the receiving end towards the source end. Yes or no? This is the distance. Yes. If that is so, the wave traveling from load to the source will have positive s direction, and the wave which is traveling from source to the load will have negative s direction. So here the first term, the term varying with e raised to plus j beta s, okay, e raised to plus j beta s is a wave progressing from source to the load, since it is traveling in the minus s direction, and the term varying with e raised to minus j beta s is a wave progressing from load back towards the source. So equation number 2 can now be rewritten as, how I am going to rewrite now? Just multiply this e raised to j beta s with the zr, e raised to minus j beta s with the zr, and if I just multiply these two bracket, final form of the expression I can get as E is equal to er upon zr, inside bracket zr, e raised to j beta s plus e raised to minus j beta s upon 2, plus j r0 e raised to j beta s minus e raised to minus j beta s upon 2. This is not j, you can just rub this part. So if I multiply this er upon zr inside, this zr get cancelled, so I am left with er. And what does this term represent? This term represent cos beta s. Why cos beta s? Why not hyperbolic? Earlier when we have calculated, it was e raised to gamma s plus e raised to minus gamma s divided by 2. At that time there was a term absent of j. That's why we have written it in the cos hyperbolic form. This time no need to represent it in the cos hyperbolic form, because it's a simple expression for cos beta s. Similarly, if I just multiply er upon zr in this second term, er upon zr will become ir into r0, j term valid here also, ir into r0 sin beta s. Sin beta s corresponds to e raised to j beta s plus e raised to minus j beta s divided by 2. If you just try to calculate, you will get this final form of this expression. This is equation number 3. Let's proceed now. The similar derivation steps can be applied for the current, and we finally get the equation for current as ir into zr plus z0 divided by 2 z0, e raised to j beta s minus k e raised to minus j beta s. So here is a minus sign. You already know the difference between plus sign and minus sign, because that zr minus z0 we can take it outside and we can put minus sign outside. So we got this minus term. The current at any point on the dissipation less line now can be calculated as ir equal to ir cos beta s plus j er upon r0. If you just multiply it, just multiply these two brackets and separating the terms containing er, ir and zr, you finally get this ir cos beta s plus j er upon r0. Why r0? Because since it is a distortionless line, we have replaced this z0 by r0 sin beta s. So this is equation number 4. But we already know that beta term can be written as 2 pi by lambda. So can we represent this equation number 4 and equation number 3 somewhere in terms of this beta? Yes, we can. So the final form of the expression for the dissipationless line, distortionless line, we can calculate E is equal to er cos 2 pi by lambda. This term corresponds to beta 2 pi by lambda into s plus j ir r0 sin 2 pi s by lambda. Similarly, I can be written as ir cos 2 pi by lambda into s plus j er upon r0 sin 2 pi by lambda into s. So this equation number 6 and 7 gives voltage or current distribution is then seen as sum of the cosine and quadrature sine distribution. Is it okay? If the line is open circuited, now what I am going to do now, if I have a transmission line, these are the final expressions now, these are final expressions for us. Okay, now if I have a transmission line which I just want to draw here, and if this is open circuited, that means there is no connection of a load. For open circuit line, zr equal to 0 or infinity? Zr equal to infinity, because for open circuit line impedance is infinity. So in this value, if I put zr is equal to 0, load impedance is equal to 0, so what value we will get? So EOC. Okay, so if I put this zr equal to 0, that means IR will become equal to 0. Yes or no? Since there is no question of the current which is flowing through it. If zr equal to infinity, that means IR is equal to 0. So in this expression, if I put IR equal to 0, so this term vanish, and I will get EOC, that is open circuited, as ER cos 2 pi by lambda into S. Similarly, for open circuit line, if I put IR equal to 0, this term vanish, and I'm left with j er upon r0 sine 2 pi s by lambda, because for open circuit current is 0 and resistance is infinite. Similarly, for a short circuit line, I will just once again draw. If this is a short circuit line, so at the load, if it is short circuited, load impedance ZR equal to 0. Load impedance ZR is equal to 0, and ER, okay, voltage across short circuit. What is that voltage across short circuit? For a short circuit, voltage is 0, current is maximum. So ZR is 0, ER is also 0. So if I put ER equal to 0 in these two expressions, ER is equal to 0 here, so this term will only remain. So IR0 sine 2 pi s by lambda. And if I put ER equal to 0 in this expression, I am left with, for the current of for the equation of I as IR cos 2 pi s by lambda. So this is ESC. SC suffix indicates short circuit voltage and open circuit voltage, short circuit voltage and short circuit current. So ESC is equal to JIR R0 sine 2 pi s by lambda, and ISC is equal to IR cos 2 pi s by lambda. So these are the expressions for voltage and current for a dissipationless line. In the next lecture, we'll see the most important bit of the topic, that is standing waves, standing wave ratio, and how to represent this standing wave in terms of reflection coefficient K. Okay, so thank you very much and happy learning.